Okay, YouTube, this is going to be a massive introduction to rational functions. We're going to talk about what they are, what their equations look like, what their graphs look like. We're going to have a discussion about their domains, ranges, as well as their asymptotes. They can have vertical and horizontal asymptotes. We're going to cover all those in this video very, very briefly. So we say let's go ahead and start by defining what we mean by a rational function. We say a rational function, the root word here is ratio. So a ratio, of course, is a fraction. We say a rational function is any function where we say its f of x is equal to some numerator polynomial over some denominator polynomial. So the important thing to recognize here is that the numerator and denominator in this rational function are polynomials. Okay, but essentially we say anything that can be written this way, like for example, 1 actually is a polynomial over x plus 1. This would be a rational function, some f of x. Or we could even say x squared plus 2x minus 3 over x minus 4. This would be some rational function. We could call it g of x. But this is what we mean by a rational function, just some polynomial over another polynomial. But the first thing we want to mention about rational functions is this. We say we have n of x over d of x, where n is the numerator polynomial, d is the denominator polynomial. But d of x is not allowed to be 0. So the very, very first thing we would need to talk about when we discuss rational functions is their domains. Okay, and domain, of course, is the set of input values that actually give us an output value back when we plug them in. And one could easily see with these two right here that I've kind of just pulled out of left field, but we say if I were to say plug in a negative 1 in the denominator here, we'd end up with this value here. We say 1 over negative 1 plus 1, we'd get this, we get 1 over 0, which would clearly be undefined. Okay, so the first thing we want to do when we discuss rational functions is their domains. We say their domains would be all real numbers except for those x values which cause the denominator to be equal to 0. So we're going to look at these three rational functions that I listed over here, and we're going to state the domain of these rational functions, but we're also going to support our answers by graphing the equations of these rational functions, which I've already graphed. Okay, so let's go ahead and take a look at this first rational function. When you look for the domain of this, of course, we're looking for any values that would cause the whole thing to be undefined. And recall, again, the only way that a whole fraction is undefined is if the basement's equal to 0, the denominator is equal to 0. So what we're going to do to find domain is essentially this. Just take the denominator and set it equal to 0. This works every single time. We say solve this for x. Not that I have to show my work here, but I'll tell you what, we say clearly when x is 1, I'm going to get an undefined value. So when we graph this, we're going to find that we have an undefined spot here. And so since, and we'll go look at the graph here in a minute, but we'd say since it has an undefined spot at 1, there's this vertical asymptote. Okay, but the clear thing that I want to point out is this. Essentially, it's defined for all x values on these intervals except for at 1. So we would say the domain of this function, after just setting the denominator equal to 0 and finding out that x is undefined at 1, is this. We say from negative infinity up to an x value of 1, and then from 1 out to infinity. Basically, the only x value we're excluding here is 1. Okay, taking a look at letter B, we say, okay, well, what would the domain of this be? I think that what we always need to do when we talk about rational functions is factor these things down. Okay, so essentially, can I factor the top, can I factor the bottom? And that's exactly what I want to do here. The reason why I say factor is because, well, first of all, domain, we're looking for anything that would cause the basement to be 0. I notice that this factors into x plus 3, x minus 3. This is a difference of two squares. Okay, in the numerator, looks like we get, let's see, 2x and x. That would give me my 2x squared. Two factors of positive 1. Looks like here, since we have a middle term adding up to be a negative, we would put, say, negative 1 and negative 1. Now, I noticed that none of these factors cancel out in the top and the bottom. That was the first thing I wanted to check. But we basically say, okay, so what is the domain of this? Well, if you set x plus 3 times x minus 3 equal to 0, of course, if these are factors, then we say, then we've got two zeros here. I won't put that there, but we say plus or minus 3 when you solve this. So in terms of the domain of this one here, we'd say there are two spots on this graph that would be undefined. So we would say the domain is really from negative infinity up to negative 3, starting up again at negative 3 and then going to positive 3. And then we say 3 out to infinity. It would basically be all of these x values on these intervals, except for at negative 3 and 3, we've excluded those. And last but not least, this is like one of my favorites here. If we factor the top and the bottom, I get on top x plus 2, x minus 2. But in the basement, we say, well, this is a sum of two squares. So, of course, sums of squares don't factor. So this is just stuck as x squared plus 36. So nothing cancels on top and bottom. That's kind of an important thing here. But also, I want to point this out. In order to find the domain, hope you're getting this, you just set the basement equal to 0 and you solve it. So x squared plus 36 equals 0. If we were to solve this, you notice, I hope, one would notice that you get x squared equal to negative 36. And so x equals plus or minus I times the square root of 36. Let me rewind that and kind of go slower here. Basically, I took the square root of negative 36, which is not a real number, but I can make this in here positive by sticking an I out front. Okay, so we say x equals plus or minus 6i. The point here is this: there are no real numbers for which this would be 0 in the basement. So basically, when we talk about the domain of this one would just be all real numbers, because I am not running the risk of actually plugging in anything that would cause the basement to be 0. So while we are on the topic of undefined spots, let's consider what we mean when we talk about asymptotes. Now, I did graph these three functions. I did say I wanted to support my answers of domain by looking at the graphs of these. So this first one here, where we said we had an undefined spot at 1, let's go take a look at its graph. And so we see our first rational function here. It's this, what we call a hyperbola, okay? And we see that it has two branches. This is actually all one graph, but you'll notice here that at x equals 1 right here, if I were to draw a vertical line through this, I have this spot where my graph, its y values are decreasing as it gets closer and closer to x equals 1. Its y values are decreasing and approaching negative infinity. And as I come in from the right side of 1, you can see that my graph is clearly, its y values are increasing without bound. And it's never going to stop doing this. But at x equals 1, this clearly doesn't exist. So this would just basically go to reinforce that this graph doesn't exist at 1. Our second graph, we said we had 2 points of discontinuity. We say at positive and negative 3. So if we were to go turn this graph on here, we say positive and negative 3. Let me get this one out of here. A little bit easier if I click on it with a mouse. But we notice here that at negative 3 and positive 3, I have these two spots where my graph, of course, again, you notice my y values, they're either increasing without bound as we get really, really close to this x value from the right or the left. And looking at 3 from the left, as I come into 3 from the left, look at my y values are going down to negative infinity. They decrease without bound. So vertical asymptotes, we've noticed here on these graphs, I guess we want to look at this last graph here. We said this had no undefined spots. No undefined spots. Take a look at its graph. But you'll notice that it's defined from negative infinity to infinity. All x values work here. So what I want to do is I want to basically define what it is we mean when we talk about a vertical asymptote and what it is we mean by a horizontal asymptote. Okay, so when we hear the word asymptote, often you hear this like imaginary line that we don't cross. Okay, and I want to kind of point this out here. In terms of a vertical asymptote, the definition truly is this. We say the line x equals a, which is a vertical line, is a vertical asymptote of this graph if the y values are either approaching positive or negative infinity as x approaches a from either the right or the left. So if I was going to sketch this in, we'd essentially say, well, here's my graph, and I've got some, say, a value right here. And so there's this imaginary vertical line, but what makes this an asymptote is the fact that, and I'm going to put in a horizontal asymptote since we're having a conversation about this here in a second. But basically, what makes it a vertical asymptote is that as my graph gets really, really close to it from, say, the left or to the right, from the right, as I approach this a value, either way, we notice that our y values either increase or decrease without bound. And I will say this, vertical asymptotes, not crossable. You cannot cross a vertical asymptote. We are going to now define a horizontal asymptote. And we say the definition of a horizontal asymptote is this. The line y equals b, which you see I have this horizontal imaginary line right here, is a horizontal asymptote. We say it is a horizontal asymptote of the graph if and only if our y values keep getting really, really close to this value b. So like if this were like b right here. You notice that our y values get really close to this value of b, but only as our x values go way far out to the right or way far out to the left. So we say horizontal asymptotes, I want to write this, can cross in the middle. When we talk about horizontal asymptotes, we're talking about what are our y values getting really close to as we go out way far out on the ends, way far out on the right, way far out on the left. So you notice that this graph right here would have a horizontal asymptote because it keeps, our y values keep approaching this value of b as we go way left and way right, but never quite get there. So for instance, on our first graph here, we say 3x over x minus 1. I noticed that, and I kind of observed this, at y equals 3 right here, you can see that our graph is getting really, really, really close to y equals 3. As a matter of fact, if I were to just type in y equals 3, whoops, get that out of there, head down here, we say y equals 3. We can see that this vertical line right here, our graph gets really close to it. So that's what we mean by a horizontal asymptote. I do want to look at this last one. This last graph right here actually has a horizontal asymptote at y equals 1. Y equals 1. And we can see that here. We could cross the asymptote in the middle, but as our ends get really far out on the left, really far out on the right, that's what we mean by a horizontal asymptote. Okay. So before we wrap this video up, what we're going to do is this. We're going to talk about how is it that you can find the asymptotes of a rational function. And this would be a good thing to write down. But the asymptotes of a rational function are given thusly. So we say, let's let f be a rational function given by this numerator polynomial over denominator polynomial. And I'll point some things out here. We say n. This is the degree of the numerator. Okay, so the degree of the numerator is n. And the degree of the denominator is kind of hard to see here. The degree of the denominator is actually m, as in Matthew. Okay, so we say where n of x and d of x have no common factors. So basically what we're saying is we've already factored the top and the bottom and nothing canceled out. They share no common factors. Okay, we can say that this is always the case with respect to vertical asymptotes. The graph of f will have vertical asymptotes wherever we have zeros of the denominator. So in other words, if you want to find vertical asymptotes, here's what you do. You set the denominator expression equal to 0 and you solve for all the x values that would cause that to happen. In other words, find all the zeros of that polynomial, which is easy. We've done that a lot. Now these right here, actually number 2, these will all concern horizontal asymptotes or lack thereof. But what I want to point out first of all is this. When you graph rational functions, you either have a horizontal asymptote or you don't. You either have one or you have none, okay? So we say it has one or no horizontal asymptote, and it is determined by comparing the degree of the numerator to the denominator, okay? So when we talk about compare the degree, we said, hey, the degree of the numerator is n, degree of the denominator is m. So we say, what if n is less than m? That is, what if the degree on the top is less than the degree on the bottom? So this could be something like x plus 1, that is a degree of 1, over like 2x squared plus 3x plus 1, something like this, you know. This would be an example of what we're talking about here. We are going to refer to this where the degree of the top is less than the degree of the bottom. We could call this bottom heavy, okay? So if we have a bottom heavy thing, that is, you can almost look at it as like when you're dealing with regular numbers here, like 7/8, you know, as a proper fraction. But if the degree of the top is less than the degree of the bottom, basically the line y equals 0 is the horizontal asymptote. That is, it's just the x-axis. I mean, that's what it's going to be. So as a matter of an example here, when we go back over here and I say, well, this was 3x over x minus 1. If I were to make the top just 3, which by the way, that would mean that it has no x, it is a degree of 0. You can see that clearly this starts to hug the x-axis here. Y equals 0 would be our horizontal asymptote of this graph, okay? So bottom heavy things, y equals 0, just the x-axis is our horizontal asymptote. Now, this, if n is equal to m, that is, if these degrees, they're equal. So that is, what if I had this expression here again, I say x squared plus 1 over 2x squared plus 3x plus 1. You notice that the degree of the top and the degree of the bottom are the same. So if that's the case, then we say it has the line y equals a sub n over b sub m, or the ratio of the leading coefficients as the horizontal asymptote. So if you're wondering where I'm getting a sub n from and b sub m, basically it just means it's the ratio of the leading coefficients. So for instance, in this example here, this rational function, the leading coefficient at the top is 1, the leading coefficient at the bottom is 2, then I would say, well, then this would have an asymptote at y equals a half. It just has to do this. So going back to this graph that we had previously, when I had 3x in the numerator, I had 3x to the first over x to the first. Let me fix this here. I'm going to put some parentheses around it. I had 3x to the first over x to the first minus 1. You'll notice that the leading coefficient at the top is 3, the leading coefficient at the bottom is 1, so y equals 3 over 1. Well, that would be the same thing as the line y equals 3. And we can see clearly that my horizontal asymptote is at y equals 3. Okay. And last but not least, and we'll confront this later on in a video, but we say if n is greater than m, we'll just leave it at this. It has no horizontal asymptote. So if this is top heavy, if this is like an improper fraction, then we say it has no horizontal asymptote. If it's bottom heavy, it's the x-axis, and we'll just call this balanced. If the degrees are balanced, all we do is compare the ratio of the leading coefficients. So that's what rational functions are. That's how you define horizontal and vertical asymptotes, and this is clearly how you find the asymptotes of a rational function.